Hello friends, in the previous lecture we learned about the radiative characteristics of plane surfaces. In this lecture we will do a couple of problems and I will introduce you to the radiative properties of materials. And the first problem that we will discuss in this lecture, we have 4 surfaces, all the surfaces are at 300 Kelvin and they are exposed to solar radiation. We have to check which of these surfaces may be approximated as gray surface. So, gray surface, what we mean by gray surface is that emissivity of the surface should be equal to the absorptivity, or emittance of the surface should be equal to absorptance of the surface. If this condition is satisfied, we can call this surface as gray. So, the surface that we have in this problem, the first surface, the distribution of absorptance, spectral absorptance is given alpha lambda with respect to wavelength lambda. We have range 3 micrometer, 6 micrometer and so on, and this looks like this. This value is 0.8 and this value is 0.3. So, the first surface basically has absorptance of 0.8 in the spectral range less than 3 micrometer and it has absorptance of 0.3 in 3 to 6 micrometer spectral range. The second surface, let us call this surface 1 and this is surface 2. Now, this surface, the absorptance of this surface is given so again it has absorptance of 0.8 from 0 to 3 micrometer range and then the range is 0.3 from 3 micrometer onwards. The third surface, the spectral absorptance is given, the value is 0.3 in the spectral range 0 to 3 micrometer, then it is 0.8 in the spectral range 3 to 6 micrometer and then again it basically is given as 0.3 beyond 6 micrometer, and the fourth surface, this is third and this is fourth. This is the fourth surface. It has 0.3 absorptance, okay, and then this is 0.8 and then we have continuous 0.8 beyond 3 micrometer. Okay. Now, if you look at the emittance, the black body emissive power in this spectral range. So, we will see that the black body emissive power of sun will be in this range. This is lambda and this is EB lambda. Okay. So, this is for sun. So, this spectral emissive power peaks in the range of 0.3 to 0.6 micrometer, and if you plot the emissive power, black body emissive power of the surface which is maintained at 300 Kelvin, it will look like this, which will peak in the range of 9 to 10 micrometer. Okay. Now, we will try to calculate the spectral the emittance and absorptance of this surface. So, we define emittance epsilon as equal to integral epsilon lambda E b lambda at surface temperature d lambda and then over sigma T to the power 4, where T is the surface temperature, while absorptance we define as alpha lambda E b lambda at the surface temperature of the sun d lambda divided by sigma T to the power 4, where T is the sun temperature. Okay. Now, if you look at if you substitute the value of alpha lambda, so we from Kirchhoff's law we have epsilon lambda is equal to alpha lambda. Okay. So, we will put this value of epsilon lambda and alpha lambda in these expressions, and what we find is that for this surface, okay, the surface number 1, the epsilon lambda and alpha lambda is 0.8 where the solar spectrum lies. Okay. So, we will get alpha value is equal to 0.8 and the value of epsilon in the 9 to 10 micron range also has the same value. So, we get epsilon is equal to 0.8. Okay. For the second surface we get alpha is equal to 0.8 and epsilon is equal to 0.3. For the third surface we get epsilon is equal to 0.3 and alpha is equal to 0.3, and for the fourth surface we get alpha is equal to 0.3 and epsilon is equal to 0.8. So, from our definition of gray surface epsilon is equal to alpha, that means total emittance should be equal to total absorptance. Our surface 1 is gray and our surface 3 is gray, okay, while surface 2 is not gray because alpha is not equal to epsilon, and surface 4 is not gray because alpha is not equal to epsilon. Okay. So, this basically gives, this example gives you an idea how can we characterize different surfaces as gray or non gray. So, surface number 2 and 4 are non gray, surface 1 and 3 are gray. Now, how do we calculate the properties of the surface? We in the previous lecture tried to find spectral, directional, hemispherical and total emittance, absorptance and reflectance. Now, theoretically how can we calculate these properties? So, in this lecture I will just briefly introduce you to the electromagnetic wave theory and the Fresnel's relation. So, basically for smooth surfaces, smooth and metallic surfaces, one can solve Maxwell's equation of electromagnetic radiation, which basically includes electric waves and magnetic waves, and based on the solution of these waves we can find out the amount of radiation reflected from the surface. Now, it depends on the magnitude of electric and magnetic field, that means it will depend on the wavelength. It depends on the complex index of refraction. You all know that index of reaction refractive index, but not everybody knows that it is a complex quantity. We have a real part n which we normally call index of refraction, and there is a imaginary part also with magnitude k. So, complex index of reaction is basically used to calculate the properties of the surface, and both n and k they depend on wavelength. Okay. So, the electromagnetic wave theory, Maxwell's electromagnetic wave theory gives us an expression of reflectance rho in terms of complex index of refraction. The two parameters are n, the real part of complex index of refraction, and k, the imaginary part of refractive index of refraction. So, the expression for reflectance rho is equal to n minus 1 whole square plus k square divided by n plus 1 whole square plus k square. Now, this gives you normal reflectance. That means, if there is a surface and it is smooth and it is a metallic surface, smooth metallic surface, the normal radiation, that means falling perpendicular to the surface, the amount of radiation reflected from this surface will be given by this relation n minus 1 square plus k square upon n plus 1 square plus k square. So, this is for the normal direction. Similar expressions exist for radiation falling at an angle. Okay, from different angles different relations exist, but the relations are little complicated. So, I will just introduce you to the normal reflectance, that is the radiation falling perpendicular to the surface. Okay. Now, this is for metallic surface. For dielectric material, the imaginary part of index of refraction is 0. So, k is equal to 0, and the expression for reflectance for a dielectric material will simply be equal to n minus 1 square upon n plus 1 square, the k is equal to 0. Once we know the reflectance of a smooth metallic surface or a dielectric surface, we can calculate its emittance, absorptance as equal to 1 minus rho. Okay. So, the reflectance calculated from the theory and experiments have very good agreement. On this slide you see the normal emittance, which is basically 1 minus the normal reflectance for some materials including metals and non-metals. So, what we see is basically the wavelength dependence of this emittance, and what we observe is that for most part of the spectrum, the metals, aluminum for example, nickel, tungsten, they have very low value, very small value of emittance. Okay. While for carbon, which is very much of interest to us, the emittance is more or less constant at around 0.9, okay, in the wavelength region, which is basically mostly useful for heat transfer applications. So, we can assume carbon to be mostly like gray. The emittance is more or less constant over the wavelength regions of interest. In furnaces, for example, in boiler furnaces, the walls of the furnaces are basically coated with the soot material, that is carbon material, and we can assume these surfaces to be black or at most gray, because the emittance of this carbon is weakly dependent on wavelength. Okay. Similarly, with silicon carbide, which has very weak dependence on wavelength, but metals metals also show weak dependence, but there is a strong emittance in short wavelength region for aluminum for example, for tungsten example. So, at short wavelength region they have a strong large value of emittance, at larger wavelength the emittance is small, but more or less constant with wavelength. Now, radiative properties of non-conductors. So, metals have free electrons and they display very high reflectance, very small value of emittance, as we have seen in the previous slide, very small value of emittance, they have very high reflectance. So, metallic surfaces are highly reflective, okay, because they have free electrons, and they also have strong absorptance. So, whatever is not reflected from the metallic surface will be absorbed strongly within the metal. So, they are very poor transmitter of radiative energy. On the other hand, non-conductors, for example, the alpha silicon carbide do not have free electrons and they do not display high reflectance and absorptance. So, very less amount of energy is reflected from non-conductors, and whatever is basically whatever energy passes through the medium is basically transmitted and is not absorbed. So, they have low value of reflectance as well as low value of absorptance. The phenomena basically governed by phonon-phonon interaction. So, in non-conductors, when radiation energy is absorbed, the energy basically excites the vibrational levels of crystal lattice, and due to this vibrational excitation, the radiation energy is absorbed. Now, the phenomena of this vibrational excitation does not happen at all wavelengths, it happens only at selected wavelengths. For example, on this figure what you basically see is a strong reflectivity and strong absorption also in the wavelength region between 10 to 12 microns. Okay. So, this material will strongly reflect as well as strongly absorb only within this small region, this is called band. Okay. So, they have what we call absorption bands or reflection bands. Okay. Other than these bands, they are virtually non-reflective, very low value of reflectance, and they are good transmitters also. So, most of the energy that is not reflected from the material surface will be transmitted. Okay. So, non-conductors are highly transparent with weak reflectance, and they have a band of high reflectance and absorptance. So, non-conductors, they absorb and reflect only within a band. Okay. And the application of such materials for the non-conducting material is basically in band pass filters. Whenever we want to devise a filter for radiation, a band pass filter, these type of materials are used because of this characteristic of reflectance and transmittance. There is another class of materials which has find much application in solar collector case, and they are spectrally selective surface. Now, what we desire in solar collectors is a type of surface that absorbs most of the solar radiation coming from all whatever direction, whether direct or diffuse, at the interest of wavelengths, some part of visible and infrared. But simultaneously we also desire that the solar surface, the collector surface should not emit much of radiation. But what we have learned so far from Kirchhoff's law, any surface that absorbs maximum radiation or absorbs radiation also is a good emitter. A good absorber is also a good emitter. So, there is a conflict here. We want a surface which absorbs radiation, good amount of radiation, but we also want a surface which does not emit much of radiation. So, in this case what is basically done is we combine the properties of more than one materials. We put some kind of coating, for example, silicon oxide coating over an aluminum substrate gives you good amount of absorptance for solar energy, which is around 0.9, but it simultaneously also gives poor infrared emittance, which is at 0.1. So, by combining the properties of this non-conducting and dielectric materials with metallic substrate, we can achieve good absorptance of solar radiation simultaneously with the poor emittance of infrared radiation, which is basically the case of the solar collector. So, we have to combine the properties, we have to combine a number of materials into a sandwich structure. Now, a similar problem, the one that we discussed here, I will discuss with the help of an example where we have a plate of metal. The metal has complex index of refraction, which is basically the real part n is 100 and the imaginary part is also 100. Okay. So, we have this metal plate and it is covered with a dielectric material. The dielectric has an absorption band such that the complex index of refraction is 2 minus I, k is equal to 1 for the wavelength range 0.2 microns and 2 microns, and it has a value of 2, that is k is equal to 0 within the wavelength range lambda less than 0.2 microns and lambda greater than 2 microns. Okay. So, all radiation within the given spectral band is completely absorbed. It is also given that all radiation within the given spectral band is completely absorbed in the dielectric. That means, in this range 0.2 micron to 2 micron, all the radiation is absorbed and nothing basically reaches the metallic surface. Okay. So, what we have to find in this problem? So, we have to determine the total normal emittance, that is epsilon, okay, in the normal direction. Okay. Okay. We have to determine total normal absorptance, that means we have to find alpha n. Okay. Okay. And that is from the solar radiation. Okay. The absorptance depends not only on the surface, but also the radiation coming in. So, let us solve this problem. Okay. So, let us first draw the diagram. So, we have vacuum at the top from which solar radiation is falling, okay. The refractive index is 0. On top of this substrate we have this dielectric material, okay, and then we have this metallic surface, okay. So, complex index of refraction m for this is 100 minus I 100, and this has a complex index of refraction that depends on wavelength, okay. So, first of all what we will do is we will apply the Fresnel's relation to find out the reflectance, okay. So, we apply Fresnel's relations to find out the reflectance, okay. So, Fresnel relation is given by rho. Now, we will call it rho lambda, because the dielectric property depends on wavelength, while for the metallic substrate it is independent of wavelength. So, let us write it in general rho lambda. So, rho lambda is equal to n minus 1 square plus k square divided by n plus 1 square plus k square. This is normal reflectance, normal reflectance, okay. Now, I will call this medium as 0, this medium as 1 and this medium as 2. So, rho 1 2 is basically the reflectance at this interface between 1 and 2, okay. So, reflectance at the interface rho 1 2 will be given by 100, the real part of the metallic substrate, minus 2. So, just like go back, 2 is the real part of the dielectric. So, 2 is the, so this will be basically the real part of the interface. So, 1 will be when we have interface with a vacuum. So, n is the medium 2. So, let us just call it n 2 minus n 1 or n 2 plus n 1, okay. So, 100 minus 2 is square, okay, plus k value is equal to 100, and then we have 100 plus 2 square plus 100 square, okay. So, this is the reflectance at the interface 1 and 2, okay. Had it been vacuum and metallic substrate, instead of 100 minus 2 I would have taken 100 minus 1. So, this value is equal to 0.96, okay. So, highly reflective, the reflectance of the metallic substrate is 0.96, okay. Now, so this is dielectric metal interface, okay. Now, we have rho 0 1, that means the interface between vacuum and dielectric. So, vacuum dielectric interface, okay. So, rho 0 1 we have a value equal to n is equal to 1. So, 1 square 2 minus 1 square plus 1 square 2 plus 1 square plus 1 square, okay, and this value is going to be equal to 0.2, and this is for wavelength region 0.222 micrometer, and the same value will be equal to 2 minus 1 square plus divided by 2 plus 1 square is equal to 0.111 for wavelength region less than 0.2 micrometer and greater than 2 micrometer, okay. So, this is going to be the reflectance at this interface. So, now let us try to find out total reflectance of this complex material. So, total reflectance of composite structure So, how do we find total reflectance of composite structure? So, let us look at it. This is our composite structure. So, some radiation basically I am going to draw it an angle just for the purpose of understanding. Instead of drawing normal direction, I will just do it at an angle. So, this is the amount of radiation that is not reflected, but transmitted from the dielectric vacuum interface. Okay. Some part of it will hit the metallic interface. So, this is metal. Now, some part of it will be reflected here, and some part will be transmitted, and then some part will again reflected and again reflected, and so on. Okay. So, there will be multiple reflections between the interface. Okay. This is the transmitted radiation at the dielectric vacuum interface. This is the reflected part from the metal interface. This is again reflection at dielectric interface, and this is again reflection. So, we define rho lambda, okay, is equal to rho 0 1. Okay. So, this will be equal to rho plus 1 minus rho naught 1 square rho 1 2 plus 1 minus rho naught 1 square rho 1 2, and then there will be a series in this rho naught 1 rho 1 2 plus rho naught 1 rho 1 2 square, and so on. So, there will be multiple reflections. So, this is the reflectance of the composite structure. Okay. So, this is the geometric series with sum. The sum of geometric series is given by, for infinite terms, 1 over 1 minus r. So, r is the value of the coefficient that we are multiplying with rho naught 1 rho 1 2. Okay. So, this series, the reflectance will be equal to rho naught 1 plus 1 minus rho naught 1 square rho 1 2 1 minus rho naught 1 rho 1 2. So, all these values rho naught 1 rho 1 2 we have calculated already. Okay. So, this value will be equal to 0.9610 for lambda less than 0.2 micrometer and greater than 2 micrometer. Okay. So, this is going to be the reflectance. Now, let us see how the total emittance is found. Okay. So, total emittance epsilon lambda is equal to alpha n lambda is equal to 1 minus rho lambda, and this value will be equal to 0.8 for wavelength region, 0.2 micrometer and less than 2 micrometer. Okay. And this value will be equal to 0.03, 1 minus 0.961, 0.390 for lambda value less than 0.2 micrometer and lambda value greater than 2 micrometer. Okay. So, this is the value of emittance we have found, and same thing is with the absorptance. So, now we find the total value, that is epsilon will be equal to 1 over sigma T to the power 4, where T is 300 Kelvin, integrated over 0 to infinity, okay, epsilon lambda, okay, EB lambda at the temperature equal to 300 and d lambda. Okay. And this value will be equal to, we have to substitute 0.8. So, we can just write 1 over sigma T to the power 4 0 to 0.2, okay. The value will be equal to 0.0390 EB lambda d lambda plus 0.2 to 2 EB lambda, this value will be 0.8 EB lambda d lambda, and then beyond this 2 to infinity, the value will be again 0.0390 EB lambda d lambda, and when we solve this we get the total value is equal to 0.039. Okay. The value we get is 0.039 for the total emittance, and similarly alpha is also calculated. I will just give you the result 1 by q solar, the solar flux upon alpha lambda Eb lambda. Now, this will be at the sun temperature, okay, d lambda. Just like we solve for emittance, we solve for absorptance 1 upon q solar, that is sigma t to the power 4, okay, upon 0 to infinity alpha lambda Eb lambda, and evaluated at the sun temperature and integrated over all the wavelengths, and this value will be coming to 0.7527. Okay. So, what we see in this example is that just by combining a dielectric sheet with a metal substrate, what we have achieved? We have achieved a total emittance which is very low, the value is 0.039, and we have achieved a high absorptance, the value is 0.7527. Had we used only metal, we have got good amount of reflectance, okay. The absorptance of the metal is very poor, okay. Had we used only dielectric, the dielectric also gives you good absorptance 0.2 or 0.1, but it also gives you good emittance. So, it will no doubt absorb more, but it will also emit more, but by combining the two, the dielectric and the material metal, we have achieved best of both the worlds, good amount of absorptance and low amount of emittance. Okay. Thank you for your kind attention.